everyone, and welcome to our video. Today, we'll explore the world of image pre-processing, which is a critical step in image analysis that prepares images for tasks like machine learning, pattern recognition, and computer vision. It includes operations like resizing, filtering, and transforming images to ensure consistency and enhance important features. In our project, we processed a set of images by applying certain filters, including a custom filter. First, we implemented this using a sequential approach and then optimized it with parallel computing techniques. This comparison highlights the importance of efficiency in large scale data processing. So, let's dive in.
And now, let's see, what do we mean by parallel computing? Parallel computing is all about breaking a larger problem into smaller tasks that can be executed simultaneously across multiple processors. Think of it as a team project. Instead of one person doing the whole work, the tasks are going to be divided among all team members, reducing the overall time required. In image pre-processing, this approach is useful when dealing with hundreds or thousands of images, where sequential processing can be very slow in this time. So we used Python's joblib library to parallelize our image filtering tasks, allowing multiple processors to work together at once.
Now let's start with the main objective of this project, which is what? Basically, we want to go from image A to image B. And to do this, we simply take the image A, the original image, and apply these set of operations from top to bottom. The top being converting it to grayscale, then we apply the Gaussian blur and the slope filter, and then we normalize the image and we clip the image, and we have successfully reached the final image, image B, in around 2 seconds. You might be thinking, good, now my job is done. But actually, you forgot to apply all of these operations to all of these set of images, which is around 200 images. And the catch is that I want you to do it in under a minute. Now you're gonna be like, how is this possible? How can I apply to 200 images the same operation which took me 2 seconds for one image? It surely will take more than a minute. However, here, my friend, is something known as a parallel computing that will help you to do the task.
Now, let's look at the parallel implementation. The idea behind parallelizing the code was to split the workload across multiple processor cores. We have used Python's library called joblib that simplifies parallelization. In this figure, we can see an example of how our parallel code works using example 3 worker processes in parallel. There is a sequential region which, upon calling the function in joblib, divides the past function work between 3 processes. Furthermore, these 3 processes come across another joblib function dividing the work to 3 more processes. Finally, once the work is done, it's joined back to the sequential region to print the final result. So let's have a look into how the joblib function works exactly and how we used it to parallelize images in our code. Firstly, joblib consists of 2 important components, one being the parallel class, which takes the number of cores as a parameter. The second component is the delayed wrapper function. The way these components work together is that, let's suppose you have a function that you want to parallelize. The wrapper function will take this as an argument and pass it to the parallel class to parallelize. Now we can see how batches of images are being processed by worker processes in parallel. Furthermore, while applying the filters function to the images, there is one function that applies a custom filter pixel by pixel to each image. This function uses the nested loop and applies for each row the filter to every column one at a time. As this is done sequentially for all the rows, we have implemented nested parallelism that will allow the rows to be executed in parallel, making the job even more easier.
Now, let's compare the results by the execution time. The sequential time was 355.17 seconds, and after the parallel implementation, the execution time was reduced to 49.20 seconds, which is 7 times faster than before. We also tested the parallel code using different numbers of cores and found out that the best performance was achieved with 16 cores, which corresponds to the maximum number of logical cores available on our hardware. Now, what does this mean? This means that we successfully achieved optimal utilization of the available resources. Also, to ensure accurate results even in parallel execution and its race condition, we use techniques such as critical sections and atomic operations. However, solving the race condition added an overhead, causing the execution time to increase to 95.82 seconds. But even with this increase, the execution time is still way faster than our sequential code. In conclusion, we can say that this project demonstrated how parallel computing can optimize resource utilization, and secondly, reduce processing time, and finally, handle scalability challenges effectively. In the end, thank you for watching, and if you found this video helpful, please give it a thumbs up.